Two-dimensional time. Probably one of the strangest ideas I've come across. Multidimensional shapes and spaces, which I talked about in my previous video, are already hard to understand and imagine. But multidimensional time? What even is that? And yet today we will at least try to approach this question. Having covered extra dimensions of space, I decided to make a direct continuation and immediately dive deeper into the topic of additional dimensions. Last time I deliberately didn't touch on the topic of time at all, and we focused only on spatial dimensions. Today, on the contrary, we'll put the main emphasis on time. So, today we'll talk about multidimensional time and about universes that may have more than one time dimension. About what this even means, what a universe with two time dimensions might look like, and more precisely, what effects this could lead to. How the concept of multidimensional time is viewed in science, and whether there are any serious theories that involve more than one time dimension. We'll talk about all this and much more today. I'm Andre, and this is Cosmos Elementary. It's hard for us to think about both four-dimensional space and two-dimensional time. And probably the main reason is that we seem to live in a 3+1D universe. That is, a universe with three spatial and one time dimension. Our species evolved precisely under such conditions, and our brain is capable of perceiving exactly that kind of universe. Though even here some scientists would argue whether our universe is truly 3+1 dimensional, and I'm not even talking about string theory. Indeed, there are studies where scientists not only discuss hypothetical universes with more than one dimension of time, but also allow for the possibility that our own universe, in some sense, has two time dimensions. We'll talk more about this in detail later. But I also think that understanding two-dimensional time is even harder than four-dimensional space, not least because the very nature of time itself sparks a lot of debate. Well, of course, space isn't entirely clear either, but time, that's a whole other story. Some even believe it doesn't exist at all. I've made a separate video about whether time exists or if it's just an illusion. Our view of time, like our view of space, has changed over time. For example, Newton believed in the existence of absolute space and time. That is, space is the place where events occur. And even if there is nothing in it and nothing is happening, space itself still exists. For him, space was static and unchanging. The same goes for time. Newton's absolute time is like a universal clock that ticks the same way throughout the entire universe. And this clock runs regardless of whether anything is happening in the universe or not. Space and time exist independently of each other, according to Newton. But even Newton spoke about time in a more, let's say, everyday sense, what we now call relative time, though I'm not yet talking about Einstein's theories of relativity. Here we're talking about how two events are positioned relative to each other in time, specifically which event happened first. You need at least two events to make sense of this kind of time. Fortunately, the universe is full of events. In the case of relative time, your head starts to hurt when you try to imagine two-dimensional time. That is, when we have just one time dimension. We can picture it as a kind of a line on which all events are placed. We are at the point called now. Before it, in order, are all of the events of the past. After it are events that are yet to happen. More precisely, this applies to a single specific moment, and in practice this now point is constantly moving forward, with more and more events ending up in the past, but still, there is nothing crazy about this. Surely each of you has some sort of visual representation of this timeline in your mind. I myself have a certain visual image of the flow of time, in fact, more than one. The first is some kind of abstract representation in my mind of all my past up to the present moment, and even a possible future. For example, planned tasks or events that might happen. It's difficult, actually probably impossible to describe in words, but in my mind it appears as a kind of an image. although there are simpler versions as well. I also still visualize the week in my mind through a school planner, and I have a kind of mental picture for the year, where the seasons and months are clearly visually separated and then the year loops back onto itself. Though this one doesn't involve a calendar. Also, I have a visual for the history of Earth, for latest centuries, Middle Ages, and much further back in time. Let me know in the comments. I'm really curious how different people imagine time in an everyday sense. But still, whether we use any mental images or not, things are more or less clear. But when we start talking about two-dimensional time, by analogy with spatial dimensions, our time axis line would have to turn into a plane. And here, events could be placed not just one after another, in a predictable sequence, but somewhere on a plane, with two time coordinates. It seems that the usual words before and after start to lose their meaning. It really is tough. By the way, when talking about this topic, we can't forget the so-called arrow of time. Even though space and time are now combined into a single concept, space-time, and our universe is called four-dimensional, 3 spatial dimensions plus 1 time dimension. Time is clearly different from the other dimensions, at the very least because it has a definite direction. Along any spatial dimension, we can freely move in any direction. For example, we walk forward, but nothing prevents us from turning around and going backward. With time, we can't do that, at least as far as we know. And the arrow of time, which I've mentioned before, is the concept that indicates the direction in which time flows. So we imagine time as a line, but we need to add an arrow at one end. That's the arrow of time. It's important to remember that it's not so simple, and there are actually several different kinds of arrows of time. One of the main arrows of time is the thermodynamic arrow, which is connected to the concept of entropy. We see time flowing in a certain direction because, on average, entropy in the universe increases. That is, to simplify greatly, order gradually turns into chaos. A plate will break, but the shards won't come back together into the plate. As a result of radioactive decay, particles, they decay rather than come back together, and so on. There's also the psychological arrow of time, which is connected to our perception. We remember the past, but do not remember the future. There is the cosmological arrow of time, and so on. The main thing for us now is that this is a characteristic unique to time, and it distinguishes time from the other dimensions. And this raises the next question. If space and time are so different, why were they combined? And by the analogy with the increase in the number of spatial dimensions, can we at least in theories talk about increasing the number of time dimensions? As I've already said, until the 20th century, space and time were considered separate, independent entities. Basically, if we look at this not from the perspective of physics, but from our everyday experience, the idea that space and time form a single entity seems strange and unintuitive. But the universe does not care about our intuition. The unification of space and time into a single concept is often associated with Einstein. And that's no coincidence, his special theory of relativity paved the way for this. However, the specific geometric interpretation of four-dimensional 3+1 space-time, where the focus was explicitly stated and based on Einstein's work, was developed by one of his teachers, Hermann Minkowski. If we want to know the location of an object in three-dimensional space, we need 3 numbers along 3 axes in some coordinate system. But all this answers the question where. In space-time, we need to add a 4th coordinate that answers the question when. Here, the concept of a world line appears, the trajectory along which an object moves through space-time. Both a photon and you have a world line. Something vaguely similar, though on a 2-dimensional map, can be seen in Zelda Breath of the Wild and Tears of the Kingdom, where there is an option to show Link's entire path from start of the game. Visualizing a world line in a full 4-dimensional space-time is already more difficult. But here again, just like when trying to understand multidimensional shapes, we can resort to simplifications and reduce the number of dimensions. A useful tool is a space-time diagram like this one. I've already used these, for example, in a video about the horizons of the universe. If we take the full three-dimensional space, it's not quite clear where to fit the time axis here. But if we collapse the three spatial dimensions into one for clarity, it becomes much easier. One axis represents space and the other represents time. Here we can already draw world lines. Here are simple examples. The first one, an object that isn't moving in space but is moving through time. Its world line looks like a vertical straight line. The second object moves through space in one direction at a constant speed, and the third in another direction. Of course, a world line can have a more complex shape. An object can change its trajectory in space, accelerate, decelerate, and stop. Here we see that time becomes a full-fledged coordinate for describing an object's position in spacetime, and each point in the coordinate system, in this case, is described by two numbers, one for each axis. And in reality, it's the same, only instead of one spatial axis, we have three. One might think that this is just some abstract trick. Einstein haters would even call it some nonsense, but no, it all has a very real physical meaning and effects in the real world. After all, for Newton, time was absolute and the same everywhere, but for Einstein, it is relative. You've probably heard about time dilation and length contraction effects, so we won't go into detail about them now, but they do a good job of demonstrating the real connection between space and time. Such space-time diagrams are used, for example, to explain why a massive object cannot reach the speed of light. One of the non-obvious things is that an object, let's say the object whose world line we see on this graph, that does not move in space but moves through time, does so very quickly, at the speed of light. We also move along the time axis at the speed of light. However, if we start moving in space, we then move less through time. And the faster we move through space, the slower we move through time. Moving through space at 100% of the speed of light would mean a complete standstill in time, which is, generally speaking, a problem. And there are also nuances regarding which observer we're talking about. And a similar time-slowing effect is caused by gravity. The stronger the gravity, that is the curvature of space, the more time slows down for an external observer. And the most extreme examples are black holes. We don't encounter black holes in everyday life, so we don't really notice these effects, even though they are present even under normal conditions. The most well-known example is of course the operation of GPS satellites. Their accuracy depends on how precisely and synchronously the clocks are set. But due to their fast motion in orbit, their distance from Earth, and the different gravitational influence compared to clocks on the ground, time on the satellites runs slightly differently. This has to be taken into account, and corrections must be made for GPS technology to work properly. Without accounting for the effects of general and special relativity and time dilation, satellite navigation would be useless. Another example I mentioned is particle decay. Certain particles decay at a specific rate, but when scientists accelerate them in particle accelerators to near the speed of light, they experience time dilation, so they live much longer and decay more slowly. These and other examples clearly demonstrate the inseparable connection between space and time. And if we have multiple spatial dimensions, then why not have multiple time dimensions as well? In general, the discussion about additional time dimensions is in many ways similar to the discussion about spatial dimensions. Here, too, we can discuss hypothetical universes within the multiverse that have not one but two time dimensions. Considering that in some versions of the multiverse, other universes are understood as universes with fundamentally different physical laws, it is at least worth pondering. Another aspect concerns our own universe. Could there be more than one time dimension in our universe? And if so, why don't we see or perceive it? Maybe just like spatial dimensions in Kaluza-Klein theory or string theories, they are simply very small. This raises questions about what such a universe would even look like and what effects might occur if our universe actually had more than one time dimension, and what if we just haven't discovered them yet? When we constructed space-time diagrams for convenience, we reduced the number of spatial dimensions from 3 to 1. If we view this as a simplified model of our universe and allow it to have 2 time dimensions, then we would need to add another time axis. Yeah, it's complicated. 2 time coordinates, a complex world line. We can try to simplify it again and for now disregard the spatial axis altogether. And we return to the view where, in such a universe, time can be represented not as a line, but as a plane. But how do we translate this situation into the real world? When a moment is described by 2 coordinates instead of just 1, there isn't much information about 2-dimensional time and how it would look in the real world, but I have come across some interesting thoughts on this subject. Maybe we shouldn't even try to understand how a hypothetical being living in a hypothetical universe with 2 time dimensions would experience the flow of time. For us, their perception of time makes no sense. Just like as movement in the 4th spatial dimension perpendicular to the 3 we're familiar with makes no sense. Perhaps to describe an event, they would specify not 1 date, but 2, to indicate the position on the plane of time. In turn, for them, our words before and after would have no meaning, and instead they might use several analogs. Something like before after, or after, before, but of course this is just speculation. But still, here we can also talk about some consequences of having 2 time dimensions that are more understandable to us. And these are the reasons why scientists generally don't like this topic very much. Yes, I mentioned that multidimensional time is discussed in science, but I didn't specify that it's hard to call this topic mainstream. One of the main, though admittedly few, theorists in this field is Itzhak Bars. He's a prominent scientist specializing in symmetries in physics and works in areas such as particle physics, string theory, and more. He developed a theory of physics with 2-dimensional time. He wrote scientific papers on the subject and even has an entire book about it. In that book, he names 2 main reasons why other scientists pay little attention to the topic of multidimensional time. Quote-unquote ghosts would have to arise. Well, in this case, ghost of course is a metaphor. By that, Bars means negative probabilities. More precisely, quantum system states with negative probabilities. In general, negative probabilities aren't an automatic deal breaker. They've been discussed for several decades. However, they can still be off-putting, hence the ghosts. But the second issue is problems with causality. A universe with 2 time dimensions could allow time travel to the past, and this brings up all the usual paradoxes related to causality. All this going back to the past and killing your own ancestor. Basically, a proper theory should not allow for that. And if a theory with multidimensional time can break causality, the link between cause and effect, then such a theory would be rather unattractive. And yet, the fact that the idea is unpopular among scientists for quite understandable reasons doesn't mean it's completely ignored in science. With its help, some scientists attempt to solve some problems of modern physics. If the idea of extra dimensions doesn't quite fit in our minds, but where it does fit is mathematics. Everyone has heard about string theory, with its bunch of extra dimensions, spatial dimensions in this case. But it always needs to be clarified that the existence of these extra dimensions has not yet been proven. And it's not certain that it will ever be. That's why string theory has many critics, and some even say it's too early to call it a full-fledged theory. It's more of a theoretical framework at this stage. The extra dimensions in string theories are needed to make their mathematics work. You can think of it as a mathematical trick. There have been cases where hints of the existence of an object or a phenomenon first appeared in solutions to equations, and only later were found in reality. But so far, experimental searches here are difficult. But why did I even start talking about string theories? As I mentioned before, there are many versions of string theory. For a long time, 5 main versions were discussed. which shared some common features but also had differences. Then came M theory, which kind of unifies these 5 theories along with so-called supergravity. But M theory adds one more dimension. However, there is still only one time dimension and 10 spatial dimensions, 3 macroscopic ones we're familiar with, and 7 microscopic compactified ones. But M theory is not the only version involving strings and extra dimensions with a capital letter. For example, there is F theory, which has one more dimension, 12 in total, and in some versions of it, more than one time dimension is used. Taking it a bit more seriously are S theory and U theory. Still, in all these cases, the extra time dimensions are more of a mathematical device and haven't really been considered in terms of how they might work in the real world, or what paradoxes they might cause. Additional time dimensions have also been tried as a way to address one of the main problems in modern physics and cosmology, the cosmological constant problem. It is one of the key parameters in cosmology, the energy density of space or vacuum energy. It is closely related to dark energy. And just to remind you, the problem with this constant is that the value predicted by current theories is much larger than the value we actually measure in reality. And the difference isn't just, say, a few percent. It's depending on how you calculate it, between 50 and 123 orders of magnitude. You might have heard that this is called the worst prediction in modern physics. So basically, either something is wrong with our theories and they need to be revised, or we're measuring something incorrectly. Or maybe there is some other reason. In this paper, authors attempted to solve the cosmological constant problem using two-dimensional time. How did they do it? They added an extra time dimension to the Einstein-Friedmann equations, solved these equations, and as a result, they found a value for the cosmological constant comparable to the values obtained from measurements. Does this mean that two time dimensions really exist? No. However, the result is interesting. At the very least, it gives the reason to think about why using two-dimensional time produces such a value, and to study the question further. A well-known cosmologist, Max Tegmark, has written about extra time dimensions. In his article, he specifically considered the question from the perspective of what such a universe would look like. Tegmark often touches on the topic of multiverses. He has a classification of levels of the multiverse, and there are 4 levels. One of the types he talks about is precisely universes with fundamentally different physical laws. Among the many universes, one can imagine those with more or fewer spatial and time dimensions. But in this article, Tegmark is less concerned with whether such universes can exist or not, and more with whether structures can form in them, and even more so, whether intelligent observers can arise. And Tegmark concludes that universes with dimensionality different from ours, 3+1, including those with multidimensional time, may be unstable, unpredictable, and generally won't function properly. Here we can again recall the discussion about the fine-tuning of the universe, which I already made a video about, and the fact that in our universe, which allows for the emergence of complex structures and life, a whole set of parameters coincided with specific values, and among these parameters is the number of dimensions. A significant part of the work on multidimensional time has already been done by the Itzhak Bars I mentioned earlier, along with his colleagues. Bars's approach is different from what I described earlier. For him, the extra time dimension is not just a small and compactified, one like in some versions of string theory. Bars writes about the following. Our 4-dimensional 3+1 universe might be just a part or something like a projection of a higher dimensional universe. Specifically, it has 6-dimensional universe with 4 spatial and 2 time dimensions. And everything we observe, he calls the shadows cast by the higher dimensional universe. Moreover, different objects or, say, particles in our universe could be shadows of the same object from the 6-dimensional universe. He gives the following analogy. A 3-dimensional object in a room can cast shadows of different shapes on the walls. So for inhabitants of Flatland, a two-dimensional universe, these shadows would appear as different entities. So maybe something like that is happening in our case too. What's also interesting is that if the two-dimensional inhabitants suspect the existence of higher dimensions, by studying the shadows, they might be able to deduce the true shape of the object. This hints that by studying our universe and its properties, we might find certain patterns and experiments that point to this higher six-dimensional universe. The idea is tempting because many phenomena in our universe could have a single source in a higher dimensional universe. This might help build a unified theory. And according to Bars, all this really could work mathematically using certain symmetries, and specifically with two-dimensional time. As Bars writes, there should be neither more nor fewer time dimensions than two. And various constraints in this version allow avoiding paradoxes and violations of causality. As you might have guessed, Bars' theory isn't widely accepted or popular, but at the same time it's not some fringe hypothesis. Further research could either confirm or refute it. So no matter how strange and possibly far removed from our everyday experience the idea of two-dimensional time may seem, it is sometimes seriously considered by reputable scientists who even develop quite detailed theories about it. But unfortunately or fortunately, it seems that this won't allow us to build a fully functional time machine. Thanks for watching, check out my previous video about 4 spatial dimensions, and if you enjoyed this one, leave a like, comment and subscribe for more videos in future. Bye!